All right. So for the lab today, it's uploaded already in the assignments. All right. So for the lab today, we are going to work on a circuit having all the active and passive components. So with this circuit, we have a resistor, we also have an inductor, and we also have a capacitor. Now, idea here is that we have two specific type of functions which requires extra configuration or extra explanation. All right, guys, please do not turn off or unplug any PCs that are in front of you. All right, which specifically has written do not touch, and the sockets with the red tape on it. All right. So the circuit today, they have this resistor and capacitor and inductor, and in addition to resistance, capacitance, and inductance, they also have two very well defined specific function which performs in an irregular way. I mean, they cannot be just used as any of the components. So one of them is a unit step function, a scale unit step function, which is a current source, and we have a switch, and then that switch comes with a very specific information again. The switch says that the switch stays open all the time. Switch stays open all the time, but at any given time, and any time when we start recording the response of the system that we are considering as time is equal to 0, the switch is turned on. So like it's off all the time. Switch is open all the time, but at time is equal to 0, it is closed. It's a closed switch. All right. So what would happen in this scenario if I have a closed switch? What happens to the current? Which path it would take? Imagine like there's a current at the top node of 48 ohm resistor. If we close the switch, what does happen to the current? Which path does it flow? The short circuit, right? Because there's zero resistance, it would prefer. So the whole dynamics of the system would change. All right. Then for the unit step function, so this unit step function is a scaled one because of the definitely the magnitude 3, plus it is again it has a specific, it's turning on in minus t fashion. All right, so it means that it stays on all the time, but any given time t it turns off. All right, it's a mirror image of the regular unit step function where it is 0 all the time before and it becomes 1 at a specific time. All right, so in minus t, this is what's happening with this function. So now when we are defining these two specific sources, one is a current source, another one is a switch, we will have to choose certain ways to kind of simulate this situation. All right, this example is from the book, and this is one of the response to the inductor current or the solution. Okay, so that's what we are actually aiming for. Any question until now? No? Okay. So let's start building the circuit. Before that, the time at 0 is the time when the switch turns on. All right. Let us assume that time is not 0. We are assuming that as time is equal to 1 second. All right. Instead of 0. Is just for the purpose of simulation, because starting at time is equal to 0, we will be looking at the beginning of the transients. So what I want to do that instead of we are looking at the plot right at the beginning, because the transients are very short-lived. So I just want to give it a room of 0 second, and I want to see the image at 1 second. So we'll just start the simulation at 1 second instead of 0. Nothing wrong with it, all right?
The current source is a DC.
Yes?
DC current.
So your step function, yes.
So it's 0, and then when t equal, I don't know, like 1 second, it will become 0. So it's 3 before and 0 after.
Yes, it's 1 before and scaled by 3, definitely.
Oh.
But at given time t, it becomes 0. All right. But again, as I said, that for the purpose of the simulation, we will not consider 0 as the time. Instead, we are taking one. We are scaling all the thing by 1 second. All right. There's nothing wrong we can do with time is equal to 0 second, but then the simulation would start at, at 0 point. So we would like to zoom and we would like to see. So what I want to do, I want to change all the time just for the purpose of simulation. I'll scale them by 1 second. All right. Implementing them is a real thing. The lecture is recording. Let's go to the Virtuoso Library Manager. New cell view. Lab 3. Example. Okay, we have 2 resistors, so I'll instantiate I into the analog library, and I'll take a resistor, and for the resistor we'll take one resistor here and another one over here. That's it. And then we instantiate an inductor. Inductor is just in line with this resistor over here. And then we have the capacitor, which is here. Okay, all 4 components are complete. Perfect. All right. Now for the unit step function, we are going to take a current source, which is a piecewise linear. Okay, so we will be choosing a specific source. We call it as a piecewise linear. So for that, again, instantiate. It's called current source, which is piecewise linear. All right, IPWL. That's the current source. It should be rotated here and in parallel with that. Okay. It's IPWL. So I is for the current, and then PWL, piecewise linear. Similarly, for the switch, we will bring the switch. So the current source looks nearly same, but actually it has more different properties, has different attributes. When we go inside, we'll look into the Q properties, we'll see that number of pair points, how many number of pair points, what do you want to do at time 1 and current 1 and time 2 and current 2. So it has different properties which you are not familiar with, at least at this point. Then we can go to the switch. For the switch, again, instantiate a switch. So the switch we are choosing here is, so the switch is, all right, here's the switch.
Wait, so we just type in switch and they should come up.
Sorry?
We just type in switch and it comes up.
There are many switches, yes, but you have to choose. There is a single pole, single switch. There is a single pole with the 2-position switch, but we are just using a general switch. All right. Now this switch is a voltage operated. All right. This switch activates at the voltage. Right. Please, I'm recording the session, listen to the instructions and try not to do it on the Cadence and do not log into the Cadence. This switch is a voltage operated switch. It means like normally it stays open, all right? But when you apply certain voltage, which is 5 or more than 5, then the switch turns on or it gets closed. Right now, it has a normal position, which is an open position, all right? So for this, we will bring a voltage source, but again, we have to choose not any voltage source, but a piecewise linear source. Because again, we have the source which turns on at specific time, stays off before that time, and turns on at a specific time, so that we can actually simulate that time is equal to 0, the switch is closed. We have to simulate this condition. So we have to use a piecewise linear source which we can program, okay, how when it should turn on and when it should turn off. So we have the capability to program the piecewise linear sources, and you will see in a minute what does that mean. So I'll go into the instantiate and I'll bring voltage source again like I, and then piecewise linear. So that's my voltage source. All right. So before connecting, let's wire the circuit first.
Piecewise linear thing.
What is the symbol for? Sorry. This one.
Yeah.
Yeah, that's symbol.
What's it called?
VPWL.
VPWL.
Voltage source, which is piecewise linear. So VPWL. Yes.
What's that thing next to the switch?
Sorry?
Next to the switch, there's like a small.
Okay, let me see. What?
Yeah, what's this for?
This one? The line, slanting line?
Also,
It's a switch, so switch should be, this is the representation of a switch.
It connects to a voltage source.
Yeah, so this switch is voltage operated. It's not a regular switch. It's not a manual switch. So this is a voltage operated switch. Okay, so when it gets voltage, it turns on. When it doesn't get voltage, it turns off, stays open.
So what is the how do we the other one for PW whatever, what is this one again?
The switch?
Yeah, it's
Switch.
Okay.
It's a switch. So the circuit is complete. We have inductor here, resistor, capacitor. Okay, so let me just bring in the
Also the same thing. It's IPWL.
That's correct. Okay, so once the circuit is completed, please do not forget to bring the ground. So instantiate and ground. For the grounding, we need one ground for the switch and we need one ground for the whole circuit. Okay? Let's just a little bit more. Okay, once the circuit is complete, then you should bring in your label, okay?
So can you show how can we control the font size of the labels?
Font size of the labels?
Yeah. Instead of making the circuit big unnecessarily, like make the whatever way we make and just control. Because sometimes like the letters are too big and they cover each other. So let's say you want to make them smaller.
I really don't know. I don't know specifically how to do it. I've never used it. But what you're saying is definitely possible. So it's just a matter of like I did not explore that thing.
But the thing is, for this there is like no tutorial or like I tried to find it online, but there is nothing.
Oh, there are many. Yes.
Quick question: why do you put a voltage source near the switch? Because in the circuit diagram there isn't a voltage source.
No, there is no, but there's a switch, and that switch is turning on and turning off at a specific behavior. So I have to simulate that behavior. So I have to come up with an idea that how I can do that. So this switch, as I said, what we are assuming that it stays off until 1 second, and at 1 second it turns on. So how can you simulate that? I mean, a switch is a switch. You turn it on. During the simulation, we have no capability to kind of, click the mouse and turn it on. So we want to automate everything. So for the automation, I have to come up with an innovative idea. So that's an idea that I've chosen a piecewise linear voltage source, and I'm going to program it now. You will see. We'll program it to simulate that condition that it stays off until 1 second and it turns on at very next moment. So it should be like this, off and then on. So for example, 1 second, it's 0 to 1 second, and actually at 1.0000 whatever 1 second it's on, just to simulate that working. All right. Any question? So there will be a tutorial. Let me see what exactly is your requirement, and I can actually search for it, because it has a
So there is a community, but again, someone also asked. There was no answer there.
So for example, you mean that C0 here, you want to make it big for this capacity?
Because when you export a picture at 4 times the resolution, that C is barely visible.
Or vice versa, when the circuit is smaller and you have many information, like they overlap with other elements.
So in that case, don't worry about that. So when you put a 4 times the resolution of an image, then when I'm looking at the image, I really expand it. I do the magnification just to see. I have to do it because with current page size that we have, the A4 page size, that it's not visible anyways. So when I'm looking at your circuit diagram, I have to magnify it, but there will be a solution for that. Now let me get that solution for you. All right. I have never used it, but I'm sure there are ways, because we can control it in so many ways. That's the beauty of Cadence. So now we go with the labeling. So I'll go with the labeling, and in the labeling we will go. We need VC as the label, so that whole node will get. I'm also going to look at the switch voltage. All right. So to see if that specific behavior is there. I'm also going to see for the labeling the voltage of the inductor. Okay, so VC, VL, and yeah. So I'll get VC, VL, and V switch. All right. So I'm going these 3 labels, getting these 3. So this is the VC, this is the VL, and this is the switch. All right, I'll do check and save. Okay, everything seems to work. Okay, now let's first of all let's put the values of this 1 by 240. So it's 1 divided by 240 farad. Inductor is 10 Henry. 10. We have 148 ohm. This is 100 and this one is 48 ohms. Okay. Now let's go to this switch first. Or before that, let me do this one first. Okay. Now this is the piecewise linear current source. In this piecewise linear, because we are looking at a unit step function, a scale unit step function, so actually we are looking at two states, a 0 state and a 1 state. So we just need two positions to define the function. So what I'm saying here, that yes, number of pairs of points I needed are 2. And then at time 1, the current is 3 ampere. All right, at time 1. Well, what is that time 1? I said 1 second. Instead of 0, we are saying that until 1 second, the current is 3 ampere. And at the next moment, very next moment, it becomes 0. So that is 1.00. I don't know, like choose whatever number, but then we have to be consistent with that number, okay? So I'm saying that at current, until 1 second, the current is 3 ampere. But at 1.00, very next moment, the current becomes 0. That's what 3 u of minus t means. Now I'm going to select this, okay? I'll say okay, and then I'll come to this voltage source now. For the voltage source, I also need two conditions, 1 and 0. All right. So what I'm saying that time 1, what is the time 1? So the source is 0 all the time. So at time 1, which is 1 second, the source is 0. And at time 2, the next very moment, I have 10 volts. What does that mean? It means that until time 1, there is no voltage. I told you this switch we are dealing with, the switch we are dealing with here, the switch we are dealing with is a voltage operated switch. All right, it's a voltage activated switch. So it activates when there is a voltage at its end. All right, so it's a voltage activated switch. This is very important, guys, because your lab assignment will have these things. This switch operates at a voltage. All right, so we have provided 0 voltage. It means it was open all the time until time 0 seconds. But at the very next moment, like 0.00001 second, the switch activates, which means the voltage was 0 all the time and shoot it to 10 volt. When it shooted to 10 volt, the switch becomes closed. So go ahead.
Why did you choose 10 volts?
Sorry?
Why did you choose 10 volts?
10 volts?
Yeah, why
Normally the switches, these kind of switches, they are activated at 5 volt. So I just chose 10 volts because sometimes it happens when you're solving a complex problem, not here, complex problem. If you have a 5 volt switch somewhere, you know, the matrix gets 0, somewhere the determinant becomes 0 and the solution becomes unstable. So this doesn't matter. It can have 5 volts, 7 volts, 10 volts, it's just a number.
Yeah.
But more than 4.
Yeah, and this type of switches only close when we provide the voltage, right?
Yeah, because look at this. This switch is normally open. If you see that, this is a normally open switch, right? So it means it will activate at a voltage. So it is showing you its current condition. Current condition is no voltage. Understand? You might have a switch
That is closed.
that is closed when you apply the voltage, and so it becomes open, right? But did you get the idea? Like when I said the properties of this thing, I'm saying that until 1 second the voltage is 0, which means switch is open. But at very next moment, and what is that next moment? When the unit step function turns to 0. I want to select the same moment, because if I don't do it, then there's a mismatch. Both unit step function is turning to 0 and my switch is turning on at the same moment. If I don't choose the same time, then there is a difference between them. All right. This is very important to get the real solution. I've spent a lot of time, because when I was doing these problems, I was choosing one time for the unit step function, I was doing some other time, and because there's a mismatch of the time, I would never get the simulation. I don't know how many hours I've spent to figure out this. Okay? So once this is done, check and save. Okay. Yes?
What's the current source like in?
Yes?
Why does it?
Why it goes to 0? Because that's the unit step function. It'll either be 1 or 0, or in this case will be 3 or 0. Okay, I'll be launching ADXL new.
So you're telling me like from the time the simulation runs, from the time the simulation runs from 0 to 1 second, it'll be 3 ampere, but as soon as it hits at 1.00001, it'll go to drop down to 0 ampere.
Yes.
Okay.
Correct. All right, we will be doing a transient simulation, so I'm choosing a transient. I can choose any time, but for this particular simulation, I know that 7 or 5 seconds is something a reasonable time. Let me take 5 seconds, or actually 7 seconds. We can clip it later. And I'll choose a conservative method. Conservative means it takes more points, do more calculations than the regular one, okay? So you will be able to see the smooth plots. So always choose conservative, okay? And then we will be choosing the parameters. What are the parameters that we are looking for? We are looking for the voltages, we are looking for the capacitor current and inductor current and the resistor current, and I'll be also looking at the current source just to verify if it is working in a manner or not, all right? Then there's one more thing regarding the current direction, guys. Please, you have to listen. That's very important. Many concepts here. So before that, let me go to the, let me choose. So you have to choose this third tab here, which means choose the variable to plot from the design, okay? So this is a way of choosing the variables from the designs, because I'm not looking at everything. I need few voltages and few currents. So I'll say that choose my parameters or variables that I would like to see from the design. For that, this is the third, and then I'll say from design, okay? From design, okay. Okay, from design, I need VC, so I'll click VC, all right? I need VL, I'll click VL. I'm also looking at V switch, so I'll click V switch. Okay, these are the voltages, 3 voltages I've selected. Now, how to select the current? Now, this is very important. For the current, we have to know how cadence works, because current has a direction, right? It either goes to ground or whatever. Now, in this specific problem, we are looking at the current. For example, IR is going into the resistor, top to down, right? Just remember for the cadence, when you want to select a current going through an element, we have to select the N terminal of the component, all right? The N terminal, and then it is selecting the current. Now, whatever end you will choose, just remember that the direction of the current will always be into the component. Into the component. So, for example, if I choose the top end, then into the component means direction down. If I want to look at if my problem here was current going upwards, then I would choose a lower node. I'll choose this node, which means again into the component and on top. Got it? This concept is very important, the current concept, because then you will get all your plots right, you get your calculations right. Any question? All right, if not, then I'll choose. So we have all the currents going down, and for the source we have a current going up. So I'll choose this current source, we'll choose the down node. For the others, we'll choose the top nodes. Got it? Any question?
Wait, can you repeat that?
I'm just saying that you see IR, IL, IC, all three are going into the components. So I'll choose the top nodes so that I have the down node. For the current source, I'll choose the down node because it will still be into the component, which will be from down to top, bottom to top. So first, select the node, the top node. Selected for the inductor current, this node, you see that circle that tells you the current. And then for the capacitor, also this one. And then for the current source, I'll choose this node because current direction is from bottom to top. So I'll choose this node, which means bottom to top. Once you have selected all of these, actually you can go and confirm that all of your items are selected. We have VC, VL, voltage of switch. We have R0 plus, L0 plus, C0 plus, and I0 plus. The plus here means actually you have chosen towards the ground. All right, you have chosen the original direction. It will choosing the other. For example, if I choose for the current source, if I've chosen the top node, it will tell me that I0 minus. Okay, that I'm choosing a reverse direction of the current. So once it is done, all you have to do here is hit the escape key. Hit the escape key and then go to your here. Go to your test, say OK. And then go to your ADXL. All of those values are now chosen, VC, VL, V switch, R0. So we've chosen everything from the design, and now I'll run the simulation. Okay, we have run the simulation. Okay, and we can always use the quick plot all here, and we'll plot all the values. Here are all the plots of each and everything. All right. Now this is what I was saying. I just need the first second so that it just settles down. I don't have to start from the top. And let me just choose 5 seconds. Okay. Now looking at that, our instructions tells us the inductor just shows us the inductor current, which runs until 2 seconds. For us, it will be 3 seconds. So I'm going to choose the inductor current only, R0, C0, I0. Here's the inductor current. Okay, so if I see the inductor current, some of the properties of the plot I showed you guys, but I'll just do it here. I'll right click, I'll choose the color. The color I like will be here, this one, and a little bit. Okay, so now if you see, we have the pointer. We can see that at the bottom, for example, current is at 1.8 seconds. The current is minus 1.16 ampere. All right, at 1.8 seconds, which is 0.8 seconds. The current we see is between 1. It's like 1 minus 1.0, minus 1.2 something. All right. And for the top one, around 0.2 seconds, we have 2.6, 2.7 ampere at 0.2. So for us, 1.2 second, at 1.2 seconds, we will have 2.6, whatever, 2.67 around this time. So we can confirm that the inductor current, and then at this time, we know that at 1.9 second it touches. All right. So at 1.2 seconds, nearly 1.2 seconds, it touches 0. So for us, 2.2 seconds, around 2.2 seconds here, it should touch 0.
Do they have the same amplitude?
Sorry?
Like, it doesn't look like they have the same amplitude. This graph and the one you get.
There's a reason. Okay. All you have to do to get more exact values, we have to do something. let me close this. They have amplitude, a very minute difference, not a big difference, but we can go here into the switch and we can change the properties of the switch. The switch now has, when the switch is closed, has a resistance of 1 ohms, which is quite a lot. So you can just turn the value into, I don't know, it just takes more calculation and system sometimes crashes, but it's okay. We can choose 0.1 ohm. That's okay. 0.1 ohm is still okay. But just because that switch turning on and the components internal resistances, if we change those values to, instead of substantial value, if we choose very lower value, it's okay. But overall, the plot doesn't have a big difference. It has very minute milliamps difference, which is okay. That's not a big deal. And I'm really not sure if the book is using some software to simulate. I'm not sure if that software is really that accurate, that has given the right values. Maybe our cadence values are still better in reality, right? Or maybe this is just plotted using the numerical method in some software which is not so much accurate. So plot all. So now looking at the plot, what I want to do, so I wanted to confirm the working of the unit step function, which was voltage of switch. Here's the switch voltage. So if you see that, this is what's happening. The voltage of switch is 0 until 1 second, and at the same moment it becomes 10 volts. Alright? So that's what we wanted. So it's 0 until 1 second, and it becomes 10 volt at the very next moment. Alright, did you get it? And then similarly, let's look at the current source. Here's the current source. For the current source, we see that it's 3 ampere until 1 second here, and it becomes 0 at the very next moment. Now even if you see here that it's not perfectly 0, it's not 0 ampere. I think it's not perfect. Oh, it's 0, okay. That's my eyes. So the current source is until 1 second, it has a amplitude of 3 ampere. For the current, you guys have to look at the right, alright? Just remember that when you want to plot both voltage and currents together, voltage will take the left side always. All the software, in reality, in engineering language, current will always take the right place, okay? So for the current, we are looking at the right side. So it's 3 ampere all the time and becomes 0 at the same moment. Okay, so we can look at all the plots. We can see that, for example, here. So I'm looking at the voltage, the current source. As the current source starts going down, I can see that the voltage of the capacitor starts swinging. All right, it goes down, but due to the damping, it comes back and it revolves around the current source until it settles down to 0. Okay? And that's a typical dynamic behavior of a capacitor. When you turn off the power source, because what is happening in this circuit, it's a very interesting thing that is happening in this circuit. So it happens that the circuit is getting a current source all the time, but at a very given moment, this current just turns off. When the current turns off, then the circuit in itself is whole. It is just using the power from the inductor and the capacitor to simulate all the functions. So that's how the dynamics, this is a dynamic circuit. It will have some transient response, and then with time, when the voltage inductor will lose all the energy on the resistors, it will settle down to 0. So that's a normal RLC behavior with no power source. And here we don't have a power source. Power source was there, but it turned off when the real function started. And this is exactly what we see in our plots. If you see voltage of inductor, exactly following what capacitor is doing. Voltage of switch is not of interest. Here's the current at the resistor. This is the current across inductor and the current across capacitor. So we have all those plots, and when you will be looking at them, there will always be a specific meaning of the plot. You are looking at the behavior of the plot. I told you the behavior, how the system is behaving. That's what you have to comment on the plots. Any question about anything? I'll at least stop the recording, right? Sections are complete. Let me stop the